Allison, and thank you all for the opportunity to participate in this event. It's a lot of fun. Today I want to talk to you about how we communicate with the Curiosity rover at Mars and how we're using an international network of relay orbiters at Mars to drastically increase the amount of information we can bring back from the red planet. So you might ask, what's so hard about talking to Mars? Well, it's all about distance. Mars is up to 400 million kilometers away. That's 10,000 times farther than your typical geostationary communication satellite is from the surface of the Earth. And if you know your 1 over r² law, that means it's 100 million times harder to communicate to Mars than to that geostationary satellite. So what we do is we take advantage of the fact that we have orbiters at Mars, science orbiters that we can use as relay orbiters. And as they fly over the landing sites, these landers can communicate at very high rates to the orbiter, and the orbiters can then bring the data back to Earth. That lets us bring more data back, and lets us do it much more energy efficiently in terms of the energy per bit. It lets us get high-rate information during critical events like entry, descent, and landing. And we can use these same radio signals to do in-situ positioning at Mars. So for Curiosity on the surface, Curiosity can talk to Earth, but only at about a kilobit per second, a very limited data rate when it tries to talk directly. But on UHF links to these relay orbiters, we can talk orders of magnitude higher. And so let me go through each of these orbiters. Odyssey was launched in 2001. It's in a 400-kilometer sun-synchronous polar orbit, and it can talk to the landers on the surface at data rates of up to 256 kilobits per second. The European Space Agency launched Mars Express spacecraft in 2003. It's in a highly elliptical orbit. We typically don't use it on a routine basis, but we're using it for critical events, as you'll see, and we use it as a backup relay asset if we have any problems with ours. And our most recent relay orbiter is the Mars Reconnaissance Orbiter, launched in 2005. It's a very capable orbiter with a very high performance imager. It also has a new radio called Electra that is able to communicate at data rates up to 2 megabits per second with our landed assets. Here's Curiosity on the surface. You can think of this as a 1-ton robot geochemist. Its mission is to explore the habitability of Mars, namely understanding the organic chemistry and the history of organic compounds at the Gale Crater site. The challenge here is getting it to the surface. You probably know about the 7 minutes of terror. We enter the atmosphere going 6 kilometers per second. 7 minutes later, we're hanging on this sky crane and being lowered on a tether to touch down on the surface. First time we ever tried this, so it was very important that we were in contact with Curiosity as it went through entry, descent, and landing. To do that, we oriented all of our orbiters so that they would overfly the landing site during entry, descent, and landing. And you can see the basic geometry here. As MSL descended, Curiosity transmitted at X-band tones back to Earth. Every 10 seconds, that would give us sort of, we called them semaphores, a signal of how things were going, but very limited data rate. On the UHF link, on the other hand, we were able to send telemetry at 8,000 bits per second, and that gave us real-time visibility into the entire course of that entry, descent, and landing. It let our mission control folks know in real time that the landing was safe, and also let people around the world know. These are some pictures of people in Times Square that were actually watching the landing on the big screen in Times Square. The other thing we were able to do during the landing was actually snap a picture of Curiosity on its parachute from the Mars Reconnaissance Orbiter using its high-rise imager. Phenomenal accuracy of this image, about 30 centimeters per pixel from that orbit. This is a picture from Sol 1 on the surface from one of the hazard cams on the belly of the rover. In the distance, you see Mount Sharp. This is a layered sedimentary deposit about 4 or 5 kilometers high that sits in the middle of Gale Crater. And we'll be climbing up that Mount Sharp over the course of the mission. Typical day in the life of the rover, we send commands in the morning. During the midday, it carries out its work. Afternoon, we send data back. Overnight, the Martian engineers and scientists at Earth plan the next day's activity, and we've been doing that for over 100 sols now. Here's a picture from the mast cam, a very high-resolution camera on the rover of the side of Mount Sharp, and this is exactly where we're going to be headed over the coming Martian year. Just for a sense of scale, that little peak in the middle there was about 300 meters high. Very exciting. Over the past couple of weeks, we've started sampling, and we're hoping to hear some of these results at tomorrow's press conference. These are 5 soil samples that were scooped into the analytical instruments inside the rover, and just beginning that process of exploring the organic chemistry of the planet. We've done a lot of support, over 300 relay contacts to Curiosity since we landed. Nearly 50 gigabits of data have been returned, and that's really unprecedented prior to prior missions. And so just in closing, this is a self-portrait that Curiosity took using the microscopic imager on the end of its robotic arm, kind of the same way your kids would take a picture of themselves with their cell phone. And on the background there, you can see Mount Sharp, where we'll be headed over the coming months. Thank you.